Hi, I'm Chris Stoner. I'm a space product manager with AWS Ground Station, and we're here today to cover getting high-resolution satellite data faster with AWS. And I have Matt from Satellogic North America and Tomislav with me today from Infinity Technologies. Today we're going to show you how Satellogic is using AWS Ground Station and our partner Infinity Technologies to get high-resolution satellite data faster with AWS. Satellogic is a leader in high-resolution Earth observation data collection, and they make satellite data more accessible and affordable so customers can solve global challenges. Infinity Technologies is a leading software provider for companies operating in the satellite industry, and they develop a software-defined radio that works with AWS Ground Station. Our planet changes every day with events like flooding, earthquakes, and even man-made changes like deforestation, and all of these are visible from space. Satellogic has created a satellite constellation that is creating a live catalog of the Earth, and it's capable of detecting these changes, and all this data is stored in AWS. Satellogic downlinks Earth observation data to AWS Ground Station using our global footprint of antennas, selecting the closest antenna to the acquired image for the shortest latency. Once the data is downlinked to AWS Ground Station, it is in AWS, and Satellogic has access to higher-level processing chains, such as with Infinity Technologies' software-defined radio, Blink, to create product that can be distributed or processed even further, such as change detection workflows or emergency management notifications, such as forest fires in remote regions. Here's an example of the La Palma volcano in Spain from September 29th. So this image shows the lava flow, and the repeat pass that happens the next day on September 30th shows the molten rock entering the sea. So how does AWS Ground Station help Satellogic? So what is AWS Ground Station? AWS develops and maintains a global footprint of antennas and infrastructure. This is antennas that customers don't have to worry about. You don't have to manage the infrastructure. You don't have to make the capital outlays to buy all these antennas and worry about high availability. All of that heavy lifting is on AWS. And again, as soon as the data hits the antenna, it's in AWS Cloud. And you have access to Amazon EC2, Amazon S3, and other AWS services like machine learning. And these allow you to do things like image detection and image classification. Image detection, is that a boat in the water? Image classification, is that forest? Is it farmland? All of these things can be done in AWS. You only pay for the time that you use. We offer transparent billing so you can forecast costs. There's no long-term contract required, so you pay only for what you use, and there's no contract or sunk upfront costs that you need to worry about. Data transfer is included, so we use the AWS network to move data from the antenna into the AWS region of your choice. This data is delivered near real time to your VPC or your AWS account in an AWS region, and that's all included in the cost of the contact. You can schedule up to 15 minutes ahead of the pass, and everything is fully automated. So we have APIs that are behind everything that you see in the console to allow you to fully automate to have a lights out experience once you're ready to go operational. We offer antennas in the following 9 locations. So moving from left to right, we have Hawaii, Oregon, Ohio, Ireland, Stockholm, Bahrain, Cape Town, Sydney, and Seoul, Korea. We also offer console locations in Virginia and Frankfurt, and we'll continue to scale locations to meet customer needs. We're built on the Amazon network, so we can deliver data across the globe, which means that you can receive a contact in Cape Town, and using the AWS network, you can have the data delivered near real time to Frankfurt. And you have data sovereignty. Your data is encrypted in transit and is not written to disk until it reaches your VPC or your AWS account. Some customers want the ability to consolidate their archive in a single region for distribution and further processing. So using the AWS network, you can have the data from all AWS Ground Station antenna locations delivered near real time to a single region, such as Frankfurt in this example. So before you can use AWS Ground Station with your satellite or satellite constellation, you must license your satellites with us. Well, some customers are able to set up licensing with Ground Station themselves. Others, like new space customers, might need some help. In September, we launched Licensing Accelerator to help customers gain an Earth Station license to use with AWS Ground Station locations. Licensing Accelerator can help you navigate this regulatory framework with various government entities. We leverage the latest information about satellite licensing regulations, and we have a team of consultants to help. Licensing Accelerator is included with the cost of the service to AWS Ground Station customers and can speed up the time it takes to get licensed to use AWS Ground Station. Once you're ready to get started, we'll give you a CloudFormation template. This CloudFormation template will set up your AWS account to schedule and receive contacts. And the template will create all the resources you need, such as an Amazon EC2 instance to receive data, security groups, and network access control lists, amongst a host of additional resources. It's quite a lot created by this CloudFormation template. But the template will speed up the time it takes for you to configure your AWS resources to schedule contacts and receive data. So you don't have to set everything up yourself. We give you a template to start. Again, everything is automated. We have APIs to fully automate scheduling, receiving of data for that lights out experience, requiring no human interaction. For example, we send CloudWatch notifications to start and stop each contact. And you can use these notifications to trigger your Amazon EC2 machine to start before the beginning of the contact and stop at the end of the contact to save cost. We also provide CloudWatch metrics. So during a contact, Ground Station automatically captures and sends data to CloudWatch for later analysis. Once you're ready to schedule contacts, you can decide how you want your data delivered. We offer streaming to EC2, but customers ask us for a way to save a recording that they can play back over and over. And we responded with S3 data delivery. Here's how that works. So starting from left to right, the data from the satellite is transmitted to AWS Ground Station as a radio frequency waveform. And we support X and S waveform bands today. When the waveform reaches Ground Station, we convert it from an RF waveform into a digital format called Digital Intermediate Frequency, or DIGIF. We can perform a recording of the DIGIF payload that can be played back over and over, and this is great for recording, archive, and for debugging purposes. This payload is then saved to Amazon S3. To receive your data streaming to EC2, you will need to select a software-defined radio from AWS Marketplace, such as the Blink SDR from Infinity Technologies. So what is the software-defined radio for? Well, in the past, ground providers fielded hardware modems at each of their antennas, and we decided instead to baseline AWS Ground Station on a digital output, DIGIF. This format follows the VIDA 49.2 standard, which makes it portable and readable by software-defined radio partners such as Infinity. And why did we do this? Well, really for customer flexibility. So you don't have to wait for hardware to be shipped to an antenna, installed by a tech, configured. Instead, your software-defined radio is instantly available, and you can take contacts within seconds. This interoperability allows customers more choice and flexibility also, as software-defined partners can create new SDRs that just work with Ground Station. The SDR vendors support various modulation and encoding schemes, and customers typically define that based on what they do on orbit, how they want to modulate and encode the payload onboard the satellite. AWS Ground Station reverses the process, and the software-defined radio will convert the DIGIF into the raw format that was more or less what was recorded by the instrument on orbit. Just like S3 data delivery, data from the satellite is transmitted to AWS Ground Station as a radio frequency waveform. When the waveform reaches Ground Station, we convert it from RF into DIGIF. And once you've selected a software-defined radio from AWS Marketplace, you can run the software-defined radio in your VPC in your AWS account, typically on the same host as the AWS Ground Station UDP receiver, called the AWS Ground Station Agent. The AWS Ground Station Agent is an AWS Ground Station component that handles receiving the DIGIF stream from AWS Ground Station and deals with ordering and error correction. Once the data is received by the ground station agent, it will write it to a UDP socket where the software-defined radio, such as the Blink SDR, can retrieve the DigiIF payload and perform demodulation and decoding steps. So once the data has been demodulated and decoded by the software-defined radio, you will have viewable product like this Satellogic image of the Ever Given container ship blocking the Suez Canal. If you remember, this container ship was stuck in the Suez Canal in March, and Satellogic's constellation of satellites was able to capture an image of it. Now I'll turn it over to Matt for a bit more about Satellogic.
Thank you, Chris, for the warm introduction. Again, as mentioned before, my name is Matt, and I'm the president here at Satellogic North America. And I have the honor of being here with you today to share why I think we're going to solve the world's greatest challenges with technology from space. Satellogic was founded 10 years ago by two Argentine entrepreneurs with the insight that humanity doesn't have a resource availability problem, but rather a resource allocation and distribution problem. We have enough arable land, water, and resources to feed and provide for the planet, but what we don't have is an accurate picture of the inventory. The trade-off between food, energy, water supplies, mass migration, and fighting climate change, it doesn't matter. Solving the problem requires a global, fresh source of data that practitioners can use to make decisions and be delivered at the right price point. At Satellogic, we build satellites for imaging the Earth, but we've taken a different approach and built satellites that are 60 to 100 times more cost-effective than our competitors. Our plan is to put enough satellites up in space to upset the current business model by collecting more surface area of the Earth every day than our competitors. We want to create a living catalog of the Earth on a daily basis, which will allow us to track changes and power the intelligent enterprise to make decisions about the world around them. We plan to achieve our goal of global daily world remaps of the Earth by 2025 with a more than 300 plus satellite constellation, and we're well on our way there. We have 17 operational satellites in orbit today, with a goal of reaching 30 by the end of 2022 and more than 60 in 2023. Unique to Satellogic, all of our satellites can collect more than 300,000 square kilometers every day, and each satellite has sub-meter multispectral imagery, full motion video, and hyperspectral, for which we are one of the only commercial constellations currently collecting space-based hyperspectral imagery. We are excited about the possibilities in the Earth intelligence market, and it is ripe for disruption. The traditional methods of collection to include terrestrial methods, airborne sensors, and Internet of Things, it's broken. The methods are inefficient, they're expensive, and OpEx is too high and near impossible to scale as well. They are part of the sensor puzzle, but they are only a small piece. Satellites are well positioned to help here as well too. Existing satellite constellations, purpose-built for governments, defense, and intelligence customers, are incredibly high resolution, but they're also super expensive. They also suffer from limited capacity issues as well too. Other small sat constellations have come into play to offer a higher cadence and a more accessible model, but with lower resolution trade-offs. They don't have the ability, however, to remap the planet at sub-meter resolution and offer customers a cost-effective solution to unlock the massive marketplace of opportunities to those massive problems we discussed earlier. At Satellogic, we've solved these problems, designing a satellite that is cost-effective, less than $1 million all in, and doesn't sacrifice on resolution nor revisit. And we're only just getting started. So how is Satellogic driving value to our customers and humanity at large? The scalability of our growing constellation, the frequency of revisits, plus low latency enable expedited access to critical imagery over active events, allowing first responders to disasters to have the most up-to-date information possible. Let me explain a little bit further. The image captured by Satellogic's NewSat-13 on September 29, 2021, reveals the flow of the Cumbre Vieja lava on the Spanish island of La Palma. The image captured by Satellogic's NewSat-11 on September 30th shows the molten rock from the Cumbre Vieja volcano entering the sea. The newly wrought peninsula on La Palma had doubled in size to nearly 20 hectares, more than 50 acres. High-resolution, high-frequency data enables units on the ground to prioritize and allocate resources for rescue and recovery with reliable and timely visualization. Let's have a look at one other example as well. The image here depicts the aftermath of a deadly mudslide in Atami, Japan. At least 19 people died in Atami on the 3rd of July this year, after days of torrential rain when the earth gave way and a mudslide swept away dozens of homes and buried roadways. The brown mass cutting through the trees in the top left of the image is the flow of the mud and the water. Several roads are buried and the tops of homes are almost visible, completely covered in mud. The mud spewed into the ocean and the brown streaking was still visible more than 9 days after the disaster, on this image taken on 12 July. The perspective gained from overhead imagery allows emergency responders, relief organizations, and reconstruction crews to benefit and ultimately better assist the people impacted by natural disasters. So specifically, how does Satellogic leverage our partners at AWS and Amfinicity to deliver mission-critical and time-sensitive data to our customers? Satellogic, with its growing constellation of electro-optical satellites, provides coverage of the entire surface of the Earth at high resolution and at an affordable price point. Next, Satellogic, we avail ourselves of the wide availability of ground stations around the world to multiply image download opportunities during each orbit at the lowest latency possible. And finally, Amfinicity is critical in our goal of delivering actionable imagery insights to our customers, enabling Satellogic to convert raw sensor data to data packets for further processing and AI and ML workflows. Our collaboration with AWS brings a number of advantages internally as well as to our customers and partners. With AWS, Satellogic can scale quickly and effectively with a click of the button as new ground stations come online. For Satellogic North America, our US government-facing business, the trust that comes with storing, processing, and now leveraging AWS ground stations deepens with our US government partners and foreign allies. Being able to use a ground station on demand, we can connect to our satellites in a dynamic way according to our users' needs for urgent tasking and image delivery. With the current 9 AWS ground stations, we can have a rapid response as seen in the following. First, this map shows how close to a capture anywhere in the world we can task to plan a satellite, highlighting the tasking responsiveness of the architecture. Second, the map here shows how much time it takes to download that imagery from anywhere in the world. And for those that can't see here very well, we're talking 20 minutes to an hour of latency for commercial satellite imagery to be downloaded and then begin processing. As an example, a customer needing a capture in West Africa can submit a task less than a half hour before a satellite passes over the area of interest. Within 50 minutes, that imagery will be available to download all the way in Sydney, Australia. It's truly remarkable. As our constellation grows and our in-orbit satellites evolve, the amount of data that we will need to download will increase exponentially. We are currently aiming at roughly 3 terabytes a day of data for the end of the year and more than 3 times that next year. In 2023, when our new constellation is deployed, we will be able to collect an entire world at 70 centimeters resolution every week. That is directly translated to the needs of downloading and storing 124 terabytes of data of imagery every day. To conclude, at Satellogic, we are democratizing access to high-resolution satellite imagery, unlocking the power of geospatial data to solve the world's most pressing challenges. Together with AWS, we will make the process of purchasing, selecting, and analyzing satellite imagery as easy as ordering an Uber or an Airbnb. So let me ask, what can the power of Earth intelligence data do for your enterprise? Thank you very much.
My name is Tomislav Nakic Alfirevic. Thanks, Matt. As Chris said, I'm Tomislav Nakic Alfirevic from Amfinicity Technologies, where we've been providing services and delivering products to the satellite industry for over 20 years now. I'm here to talk about Blink, our software receiver, what it does, and how it helps bring Satellogics scenario come alive. Before we get into that, for the uninitiated in satellite communications and radio communications, a typical satellite receiver consists of 3 parts. The first part is the digitizer. The digitizer transforms the analog signal coming in from the satellite into a digital representation. This digital representation is then fed into a component called DSP, or Digital Signal Processor, which demodulates and decodes the signal, basically looks at the waveform and says this looks like symbol A, symbol B, symbol C. And this sequence of symbols is then effectively forwarded to the third component, the front-end processor, which performs frame and packet level processing, stream analysis, and reporting. The final product of coming out of FEP is very close to the original raw data stream coming in from the satellite. A key property of all 3 components is that they are completely independent. They can be deployed together as a whole, or they can be deployed with third-party components. And here we're not using the digitizer because AWS ground stations come with their own digitizer. Rather, we are deploying our pure software components, the DSP and FEP, into the AWS cloud. Now, the software receivers have been around for a long time, and for 10, maybe 20 years. And they basically, there's a laundry list of desirable features that they have. They are very easy to deploy. They are extremely configurable, rapid to develop, provide a lot of licensing flexibility, handle complexity well. In general, they lend themselves very well to construction of robust multi-mission receivers, but they're not mainstream. And the reason they're not mainstream is that they typically top out at about a few megabits per second of output throughput. There's a performance limitation, a performance bottleneck. Blink is specific in that one of its key features is it pushes the envelope on output throughput, and it doesn't push it to 10 megabits, not even to 100 megabits. It pushes the envelope to a gigabit per second. And this is an absolute game changer. I'm going to go into a bit more in detail. So brace yourselves for acronym overload. The 2 protocols in use in satellite communications are CCS-DS and DVB-S. Blink supports them both. CCS-DS is more NASA, ESA, traditional large agencies. DVB-S is more in use by new space operators. As I've mentioned, Blink supports very high-speed reception, so we've measured just over 1.2 gigabits per second end of 2020, which allows Blink to not only support S-band reception, narrowband channels, but also support X-band reception channels up to 400 megahertz in bandwidth, which is really significant. Blink supports the usual suspects with regard to modulation and coding schemes used by these 2 protocols. And in difference to most other receivers on the market, it supports not only constant coding and modulation, but also variable and adaptive coding and modulation. This is significant in that adaptive coding and modulation effectively means it allows the satellite to adjust modulation and coding live during transmission to optimize transmission for current reception conditions, and the receiver seamlessly switches from one modulation to another without losing sync. This makes it possible to really make the absolute best possible use of available spectrum, given the current transmission reception circumstances. Blink is big on standards. It uses Vita 49.2 for ingestion of digitized input signals. It provides REST interfaces for monitoring control, provides XML configuration files. So it's a really nice, clean, easy to integrate set of interfaces. It runs on Linux, provides a web user interface, a very advanced user interface that runs on any device that's accessible on any device you care to access it from. And it comes with a host of other features that we sadly can't spare the time to go into right now. Now, Blink fits into the AWS cloud really well, primarily because it's a software-defined radio. In difference to conventional high-performance software receivers, satellite receivers, which suffer from a slow development cycle, low utilization levels, high deployment cost, limited scalability, high maintenance costs, much more rigid. Blink is a software-defined radio. And Blink doesn't really care if your satellite is in low Earth orbit, medium Earth orbit, geosynchronous, lunar for that matter. Blink will receive and demodulate the signal. It doesn't care if it's a narrowband transmission, a wideband transmission, something in between. It has it offers the kind of scalability that allows it to work in all of these scenarios. Doesn't really, supporting both CCS, DS, and DBS. Choose your protocol. So Blink, in short, is not a project for a specific mission or a specific constellation or a specific client. Blink is a product built for the Earth observation market. In a true multi-mission solution. And at a lower level, it fits in nicely in the AWS cloud because it understands the language of AWS ground stations, the format of data coming out from the stations, the DJI format natively, so seamless connection there. It's available as an Amazon machine image in the AWS marketplace. So it's really easy to spin up a VM and have it up and running really quickly. It runs in your VPC where it's nice and safe and under the customer's control, and it really shines when it comes to scaling. So if you start with a single proof of concept satellite, you might be using narrowband transmission. It might be just occasional. Fine, great. You just instantiate a more modest server when you need it, for as long as you need it. You're optimizing cost. You get the results that you need. Great. When you're ready to evolve your satellite, you might have version 2.0, which uses wideband. You use the same AMI. You just instantiate it on a more capable server, and you're done. You build up to a constellation. You want to use multiple ground stations at the same time, perhaps all AWS ground stations at the same time. You just instantiate multiple copies, so multiple instances of the AMI, set up data streaming to stream the data from the ground stations to these machines, and you're done. This type of scalability is absolutely unprecedented in the Earth observation industry. Nothing remotely like it has been possible so far. In addition, Blink supports pass-through mode for operational use where latency is important. It also supports store and forward mode, which is really, really useful in assembly integration testing mode, where you want to have a recording of a signal and you want to process it many times over to tweak reception parameters, to understand reception anomaly, etc., etc. So very useful there. And all of what I've said so far is kind of within the context of the AMI. And the AMI is a great package for customers who have the resources, the manpower, the time to integrate Blink into a broader system with their own orchestrator, downstream components, etc. It makes for a really nicely custom fitted solution. However, there are users who don't have the resources to do this or don't need to do this, who want a more streamlined experience. So for those kinds of users, Blink also comes in a SaaS format. So with the idea of simplifying the experience of using Blink as much as possible. And what does that look like? Basically, a user will access a web page, select the mission they're interested in. They'll get a list of passes over AWS ground stations over the next several days. The user chooses the pass they're interested in, so the contact, and schedule it. Click schedule and done. That's basically it as far as what the user needs to do. Everything else Blink does: instantiating VMs when it's time, shutting them down, storing output to S3 or wherever the user needs it to go in the meantime, optimizing cost, all done automatically. So a really simple way to get started with perhaps smaller missions, prototype missions, and so on. And the final piece of the puzzle is the way that Blink helps bring Satellogic's scenarios come to life. First of all, Satellogic uses DVB-S2 for space-to-ground communication. Blink supports it out of the box very well, so that's kind of a running start. Second, Satellogic's satellites are equipped with sophisticated sensors which generate significant amounts of data. And this data is most valuable when it's fresh. So the data needs to be brought down to the ground as quickly as possible. So Blink's ability to process at gigabit level throughputs is really important for Satellogic. Adaptive coding and modulation is another step in this direction too, that optimizing of transmission reception parameters live during a transmission to make the absolute best use of current channel conditions. Blink runs in Satellogic's VPC, providing Satellogic full control of the environment and the ability to integrate it with their orchestrator, with downstream processing software components, making for a really safe environment where the data is fully and completely under Satellogic's control. Blink's ability to run in near real-time streaming mode is really important in emergency response situations, some of which Matt just touched upon. So when there's a forest fire or an earthquake or a flood, having data that's 5 hours, there's a huge difference between data that's 5 hours old and that's half an hour old. Data that's fresh is really actionable and directly translates into saved lives and property. Over the course of this summer, we've engaged in a robust test campaign with Satellogic and AWS with the two teams, and Blink's state-of-the-art, I can say, diagnostic capabilities have really helped there in the richness of providing information to identify root causes of any anomalies really quickly, to be able to tune and optimize, quickly to iterate, and once everything's running correctly, to really provide confidence that everything is in fact exactly as it should be. Finally, Blink produces compatible output with Satellogic's downstream components, so a seamless connection there. And with that, I hand it over to Chris for the demo.
Thank you, Tomislav. So now for a quick demo of how the Blink software-defined radio working with AWS Ground Station, is able to demodulate and decode a contact that we took from a Satellogic satellite on orbit. From the AWS Management Console, open up all services, scroll down to Satellite, and select Ground Station. If you've onboarded with the service, you'll have the ability to reserve contacts immediately. If you haven't onboarded yet, simply follow the instructions on the onboard satellites page. If you need to get your license still with Ground Station, you need assistance, you can use Licensing Accelerator and follow the instructions on that page. To schedule a contact, select your satellite catalog number. In this case, I'm using Aqua. Select a date and time for the visibility range that you would like. You can also select certain ground station locations, and then a visibility window will show. Select a contact window that you'd like, a visibility that you'd like for your satellite, and select Reserve Contact. As soon as you reserve the contact, you'll be able to see it in the scheduled window. And once the contact is completed, you'll see it in the completed list. This video shows Amfinisy Technologies Blink software-defined radio receiving and processing digital intermediate frequency from AWS Ground Station for a Satellogic contact. The user interface shows live parameter readings such as ESNO, sample rate, bit error rate, number of corrected frames, and the current ModCOD or modulation and encoding scheme. There's a live spectrum display as well as a live constellation diagram. The diagrams show clear reception, noisy, and then clear again. This is a completely configurable user interface displaying any number of parameters in any arrangement. You can drag and drop each of the charts to define the user interface in a way that's useful to you. This video shows the Blink software-defined radio summary of the processing information at both the frame and packet level. It gives you an idea of how the reception went. There's hover over explanation of elements of the report and a processing timeline for visual correlation of events and measurements during reception. There is signal frequency shift due to the Doppler effect, and there's zoom and pan features in the timeline. You have the ability to get basic info on hover over for individual measurements and events. If you click the timeline event to get very detailed low-level information explaining each event. There's general report navigation, and transport stream level processing summary. And finally, here is the orthorectified image from Satellogic for that contact. This shows the Al Dhafra airport from the Satellogic constellation. Now, how to get AWS Ground Station. AWS Ground Station is available in 9 locations, with more coming soon. We also have wideband DJI-F in preview. It is in preview in a couple of locations. You can talk to us later about those locations and how to get onboarded. Wideband DJI-F opens up higher bandwidth, allows you, of course, to use software-defined radios, and this also opens up multi-carrier use cases. Licensing Accelerator is available today in the Ground Station console, and data delivery to S3 is also available today in the Ground Station and in the API. You can see the link, AWS Ground Station link, for more information on how to get started. How to get Blink. So the Blink software-defined radio from Amfinisy Technologies is available today in the AWS Marketplace. You can use this QR code as a quick link to get there. And you can try AWS Ground Station today, even if you don't have your own satellite on orbit. So today we use public broadcast satellites like Aqua, Terra, SNPP, and JPSS satellites from NOAA and NASA that are on orbit that will allow you to do your own contact. So you can download from one of these satellites and watch the data flow from the satellite through the antenna to your EC2 instance, and you can even do some upstream processing, or you can deliver to Amazon S3. The two blog posts on the screen will walk you through how to set up and run this public broadcast satellite contact on your own in your own AWS account. The first one is for Amazon S3 data delivery, and the second is for streaming to EC2. So definitely go give it a shot. And thank you so much for joining us today.